In the world of calculus, a derivative is a fundamental concept that measures change. Imagine you're driving a car. Your speed, which is the rate at which your distance changes over time, is a derivative. It tells us how much our distance traveled changes with each passing moment. Derivatives are essential tools in mathematics because they allow us to analyze how quantities change. They help us understand the instantaneous rate of change, or in simpler terms, how a function is changing at a specific point in time. The concept of a derivative is widely applicable in various fields. For instance, in physics, we use derivatives to calculate velocity and acceleration, while in economics, they are used to model marginal cost and revenue. Understanding derivatives provides us with a powerful lens through which we can analyze and interpret the world around us. Whether we're studying the motion of objects or the behavior of markets, derivatives are essential tools for comprehending change. Let's delve a bit deeper into the world of derivatives. When we talk about the derivative of a function, we're essentially talking about its slope at a particular point. Picture a graph of a function. The derivative at any point on that graph represents the steepness of the curve at that exact location. A steeper curve indicates a larger derivative, implying a faster rate of change. To calculate a derivative, we use a set of rules and formulas. These rules allow us to find the derivative of various functions, from simple linear equations to complex trigonometric functions. The ability to calculate derivatives empowers us to solve a wide range of problems. By understanding how quantities change, we can optimize processes, predict future behavior, and gain a deeper understanding of the systems we study. So far, we've primarily discussed functions with one variable, like the distance traveled as a function of time. However, in many real-world scenarios, functions depend on multiple variables. Consider the temperature of a room. It can vary depending on the time of day, the outside weather, and the use of heating or cooling systems. In essence, the temperature is a function of multiple variables. Working with functions of multiple variables requires us to expand our mathematical toolkit. We need a way to analyze how these functions change concerning each of their variables while keeping the others constant. This is where partial derivatives come into play. Understanding functions with multiple variables is crucial for modeling complex systems. Whether we're studying weather patterns, economic models, or engineering designs, the ability to analyze functions with multiple variables is essential. Section 4. Partial derivatives. A simple explanation. Partial derivatives provide a way to examine the rate of change of a multivariable function with respect to one variable while holding the others constant. In simpler terms, it's like looking at how a function changes when we only tweak one of its inputs at a time. Imagine you're holding a glass of water. If you tilt the glass, the water level changes. This change in water level can be thought of as a partial derivative. It tells us how the water level changes with respect to the angle of the glass, while keeping other factors, like the amount of water, constant. Partial derivatives are denoted using a slightly different symbol than regular derivatives. Instead of the usual d for derivative, we use the symbol to represent a partial derivative. This simple change in notation signifies that we're dealing with functions of multiple variables and are interested in the rate of change with respect to one variable at a time. Section 5. Calculating partial derivatives. A step-by-step guide. Calculating partial derivatives is quite similar to calculating regular derivatives. The key difference is that we treat other variables as constants when differentiating with respect to one. Let's say we have a function z equals f of x and y. To find the partial derivative of z with respect to x, denoted as zx, we treat y as a constant and differentiate the function with respect to x, using the usual rules of differentiation. Similarly, to find the partial derivative of z with respect to y, denoted as zy, we treat x as a constant and differentiate the function with respect to y. By following these simple steps, we can calculate the partial derivatives of multivariable functions and gain insights into how these functions change with respect to each variable. Section 6. Illustrating partial derivatives, real-world examples. Let's illustrate the concept of partial derivatives with a few real-world examples. Consider the area of a rectangle, which is given by the function a equals L times w, where L is the length and w is the width. The partial derivative of the area with respect to length AL tells us how the area changes as we change the length while keeping the width constant. In this case, AL equals W, which means that for every unit increase in length, the area increases by the width. Similarly, the partial derivative of the area with respect to width, AW, tells us how the area changes as we change the width while keeping the length constant. Here, AW equals L, indicating that for every unit increase in width, the area increases by the length. These examples demonstrate how partial derivatives help us understand the relationship between a function and its multiple variables, providing insights into how the function changes as we vary each variable independently.